Hey, feeling good, like I should. When in dark, I walk around the neighborhood, feeling blessed.
Alrighty, let's take a look at our homework for lesson 7.1.2. Our M&Ms are describing the line of best fit. Okay, so here's a great example of the line of best fit. You've got data. I don't know what the X data, what the independent variable represents, and I don't know what the dependent variable, the Y values represent. It's not labeled, but we do see a scatter plot, and there does appear to be a pretty strong correlation, a positive correlation to that data. The closer the scatter plot gets to a straight line, the stronger the correlation is. And so it makes it a little bit easier to identify the line of best fit that would pass right through and like serve as a median. Remember, it's got to flow with the data, go at the same kind of an angle, same slope ratio. And then once you've got, you're pretty confident about your line of best fit going through the middle of that data, then you identify the y-intercept and the slope ratio of the line, and that equation or rule kind of defines the entire situation, okay? So the closer that these dots, these points on the scatter plot get to a straight line, the more confident you will be about your rule defining that situation, and more confident you'll be about the predictions that you make about some of these numbers that are up here. If you had a lot of other points out here, like here, 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 now there's still kind of a flow going in that direction, but it is really weak. And to say that this is the line of best fit for all of this with, you know, you got a few outliers almost, it seems like, then that's going to be, you know, a very weak association, and your rule is not going to be as accurate as it would be if it were stronger like this. Okay, so what we do is we take data, we plot it on a scatter plot or a coordinate grid, and then we look to see what the flow of it is, and then we insert a line of best fit and use that line and the rule associated with that line to help us solve problems. All right, so here we go. Nate and Rick, we're still talking about cars. Nate claimed that cars with more horsepower were more expensive than cars with less horsepower. His reasoning was that his 300 horsepower sports car was worth more than Rick's 120 horsepower small economy car. To investigate Nate's claim, the boys looked up information about their friends' cars. The table at the right shows the results. Okay, so these are the horsepowers of different cars, and these are the prices of those cars. So we're saying that horsepower affects the price. So this is our independent variable, and the price depends on the horsepower. So this is the dependent variable. So does the information in the table support Nate's claim? And it says no. What is that supposed to know? Cars that cost more do not always have the higher horsepower. Okay, so where's an example of that? Where would be something with a high horsepower, like this guy right there? That's not really an expensive car. This one's got a much lower horsepower, but it costs a lot more money, okay? So in this situation, we are seeing that there doesn't really appear to be a strong correlation. Like, would you say that a line of best fit could go through here? Because that would suggest that the higher the horsepower, the lower the price. That doesn't make any sense. Would you say that this defines the line? And it's like, no, you got this as an outlier up there, and it's just way too weak. So at this point, you start to get to the point where you say, no, there is no correlation. It's so weak that you can't even really know for sure which direction the line is supposed to go. So there's our answer. There doesn't appear to be a correlation between horsepower and price. Then it says, look at the scatter plots for problem number 18 and use your experience to decide which statement fits each scatter plot. Okay, so remember this one, as x increases, y increases. This one, as x goes down, y goes down. This one, there's really no correlation at all, right? It's scattered all over the place. And this one is one where x increases like as time would increase, but there's a range or fluctuation of highs and lows, but it never goes too low and never goes above. So basically, you got limits here. There's a lower limit, it never goes below it, and there's an upper limit, it never goes above that. So let's read through these problems and see which ones appear to follow with these scatter plots. It says a city's average temperature January, or average daily or daytime temperature in January, and its latitude. Oh, goodness, we need a geography lesson here. All right, so hold on for a second. All righty, here you go. Here's a globe, and here's the North Pole right here, right? There's Greenland, there's the United States, there's Canada, there's Africa, Europe, blah, blah, blah. All right, so the equator is, I believe, this guy right there. If that's not the equator, this is. Hold on for a second. What are these? 15, 30, 45, yes. 60, 75, 90. So 90, 90 degrees represents the North Pole. So these are the latitudes. So what happens as you get closer to the North Pole, it gets closer, or it gets colder, right? And so as the latitude lines increase toward 90 degrees, you expect the temperature to go down. So that's the one where, that's graph 2. So as x is the latitude, right, going from 0 to 90, the average daily temperature is going to go down. It's warmest at the equator, and then as you get toward the North Pole, it gets much, much colder. So that would be graph number 2. And by the way, I just need to tell you guys something that's phenomenal. If you ever ask the question, which of the United States is closest to Africa, you know what the most common wrong answer would be? The most common wrong answer is Florida, which is right here. But technically, Maine, which is right here, is actually closer to Africa than any of the other states. Who would have ever thought that? Maine, the state of Maine is closer to Africa than any other state in the United States because of the curvature of the earth. So there you go. There's proof for it and a little bit of useless knowledge for you to take with you today. All right, part B. What weight of a car and its speed in a traffic jam on the freeway? Okay, so the weight of the car and its speed. Okay, so if you're on the freeway, as your car gets heavier, you're still going at a constant speed, right? So you know you got your speed limit, which you're not supposed to go over 65 or 70, but you really shouldn't go below 55 either, because then you're going to start holding up traffic. And so 4 is the best answer for this. The number of pets a student has at home and his or her grades. Okay, so some of you might have thought that for B, that 3 would have been the best answer, because what does the weight of the car have to do with the speed? Oh, in a traffic jam. Okay, so in a traffic jam, yeah, okay, I get it. It still doesn't seem like it should make much sense. So if you said 3 for B and C, I would kind of accept that as an answer, because that's a bad example. Okay, so anyway, this is one where it's clear that there's absolutely no connection at all, or no correlation between the independent and the dependent variable. What would the number of pets that you have in your house have anything to do with your grades? One has nothing to do with the other. So that's where you would have a scatter plot, right? It's all over the place. You have someone with great grades and lots of pets, or someone with great grades and only 1 pet or 0 pets. It doesn't make any difference. And then D, the cost of a person's home and the value of his or her car. All right, so this is kind of interesting in that sometimes people are house poor, where they buy a house, but they really want to buy a nice house, and so they overspend, so they don't have any money for anything else. And so they might be driving a less expensive car. So periodically, I'm going to go ahead and put in an outlier here where someone, the price of their home and the value of their car, someone might have a situation like that where they paid so much for their house that they can't afford to buy a nice car. But that is an outlier situation. Most of the time, if people have enough money for a nice home, they probably also make enough money to drive relatively nice cars. Okay, so that would be graph number 1, where that would tend to be the case. Of course, you might also have someone who drives a Ferrari and they spend all their money on their Ferrari, so the only home they can afford is a trailer. That's unlikely, but it could happen. No, it would never happen. That's just crazy. Yep, there's our globe. All right, now match the system of equations in the left column with its solution in the right column. All right, so you could do one of two things. You could solve each system and see what you get for an answer, or you could take these values for x and y and put them in here, here, and here and see which ones that they work in for both of them. For instance, for this one, if you took x was equal to 0, then that would become 0 minus y is equal to -4. That would equal 4. So that works for this one, but does this work for the second one? What is 0 plus -4 equal to? That is certainly not equal to 5, so no, that doesn't work. 1 does not work for this one. And so you try it in the next one, you try it in the next one, turns out it works for this one because 0 is equal to -4 plus 4, and then what does this become? 0 plus -12 equals -12? Yes, it does. So these guys match. Then try the 3 and the 7. Try it here, then try it there. Turns out the 3 for x works in this one and the 7 for y. So this becomes 15 minus 14 is equal to 1. And then 7 has to be equal to 2 times 6 is 3 plus 1. Yes and yes. That means this guy matches that one, which means you have no choice but to match this guy with that one. All right, use the rectangle to the right to answer the following questions. Find the area of the entire rectangle. So this is actually a problem for us to take 10 times 17. So our answer should be 170, right? 12 plus 5 is 17. 6 plus 4 is 10. But you can break it up into parts. I don't know why they would break it up like this. This seems kind of weird. It seems like it would make more sense to say instead of 10 times 17, make it 10 times 10 plus 7. So you do 170 makes 170. But I know what they're doing here. They're getting you ready for when we take and multiply x plus 3 times x minus 4, where you'd have the x times x is x squared. You'd have the x times the -4, which is -4x. Then you'd have the 3 times the x, which is positive 3x. And then the 3 times the 4, which is -12. And you end up with x squared minus x minus 12 ends up being the answer to that. Hooray! So you get to do that in high school. We're not going to do that yet. But this is setting you up for that kind of a process. So 6 times 12 is 72, 6 times 5 is 30, 4 times 12 is 48, and 4 times 5 is 20. Add all those together, I guarantee it's going to be 170. And now what is the perimeter? Well, this is 10, right? And this is 17, so this is 10, and this is 17. So 34, 44, 54 ends up being your perimeter. Evaluate each expression below for a when a is equal to 2/3. So this becomes 24 over 1 times 2/3. This becomes 3 over 1 times 2/3. This one can't be done because you can't ever divide by 0. So there's no answer. It's just undefined. And this one is where you take 0 and divide it by 2/3. So let's do some cross canceling. This is 8, that becomes a 1, so 8 times 2 is 16. This cross cancels, leaving you 2 over 1, which is 2. And this, 0 divided by 2/3 is the same as 0 times 3 over 2 because you multiply times the reciprocal, and anything times 0 is 0. So any division problem where you're taking 0 divided by a number will eventually give you 0 for an answer. All right, let's interpret this circle graph. The school library has 6,500 titles in its library, in its collection of books, magazines, and reference materials. The librarian is presenting information about the library to a parent association, and she has made this graph here at the right. Okay, so are they going to ask us what the nonfiction percent would be? I think so. According to the graph, what percent of the collections are nonfiction? Well, we have to add these together. So you got 20, 30, 75, and 82. So the rest of it has to add up to 100. So this must be 18% because 18 plus 82 is 100%. Would the librarian have represented this in a histogram? And the answer is no, because it's non-numerical. We're talking about sections, not numerical data that you could find an average for or a mean for or put on a number line. Okay, so no histogram, but you could use a bar graph. Remember, bar graphs and circle graphs are perfect for the categorical data. And then how many of the books are fiction? All right, now we get to use some proportional reasoning. We know that fiction makes up 45% of the books. So we're going to figure out what is 45% of 6,500. Now, there's a couple ways to do this. You can change this to your multiplier and take 6,500 and multiply it times the decimal equivalent of 45%, and that will tell you our answer. Or we could set up our percent proportion where our total is 6,500. We're trying to find the part, and we know that the percent is 45 out of 100. So cross multiply, you end up with 6,500 times 45 is equal to 292,500, and then take that and divide it by 100, and you get 2,925. Now, let me show you the correlation here. We're still going to multiply the 6,500 times 45, but I'm dividing the 45 by 100 first and changing it to 4,500, then multiply it times the 65. So we're going through the same processes of multiplying and dividing. It's just the order in which we do it. Here we divided by the 100 last. Here we're doing it before multiplying. So either way, you're going to get that is the number of books in the fiction section. And that is it for our homework. Hooray. All right, let's move on to the next activity.
Hey, feeling